turned on still.
Test. That's good volume. What do you want? A little higher? Okay. Okay. Why am I getting there? Okay. There we go.
Okay, so the last speaker for the day is Aron Wall from University of Cambridge, going to Syracuse.
All right. Thank you so much for it's really feels very meaningful to be at this event to honor Ted. So I originally gave this talk at a 50-year celebration of Hawking's paper on Hawking radiation at the Department of History and Philosophy of Science at Cambridge. So it's there's going to be more words here than equations. So hopefully some of the people who were zoning out in the other talks maybe can still get something out of this. So I'm going to talk about some like it hot, some like it cold, why the Hawking info puzzle still isn't old. Now, the TED is always very specific about people should not say Hawking information paradox, they should say Hawking information puzzle. So I've in addition to it scanning better, I've made sure to put puzzle here for TEDFest. All right. However, it turns out that TED does not control the media. And growth mindset, yeah, okay. And as of the time, I took a snapshot the first time I gave the talk to see, what people are saying about the information puzzle, and apparently the media debate is, has the problem been solved or not? So what I want to indicate in this talk is to give my own personal opinion of what questions have been solved and what questions have not been solved. Okay. So I think before we get into the specific questions that the information puzzle is about, I think maybe there's an prior aspect of black holes that maybe you could fundamentally attribute why they're such strange objects to. And that is the way in which a black hole is both hot and cold at the same time when viewed from different perspectives. So in the picture of an Eddington-Finkelstein type diagram, the Hawking radiation peels out from the horizon, as shown by these orange null geodesics, and the partner radiation falls in towards the singularity. And so the question of perspective is, we could take one perspective where we're an observer hovering outside the horizon and we can't see anything inside the event horizon. And from that perspective, the Hawking radiation appears like a hot thermal atmosphere. And although in order to be called Hawking radiation, the stuff has to escape out to infinity. If you go close to the horizon, there's a thermal distribution of all the modes. It's just the ones that have high angular momentum tend to fall back in, whereas it's only the ones with low angular momentum that escape. But they're all thermally excited near the horizon. Okay, so from this perspective, the black hole is a hot system, and it seems natural to describe it using thermodynamics. And by natural, I mean that the community was dragged kicking and screaming into believing it very reluctantly, but now we find it natural. Okay, but on the other hand, if we consider the perspective of an infalling observer who sees also a portion of behind the horizon, then the infalling observer sees something very near to a vacuum state. And I won't say exactly because the at large scales, we have curvature and lots of other things, but at short scales, we have the equivalence principle, and we expect that the state which is entangled between the Hawking radiation and the partner radiation, this entanglement just looks like the entanglement everywhere if you zoom in at a point and look at the short distance correlators. So from this perspective, the black hole is cold. So it seems to me that the tension between these two pictures is what has been structuring a lot of the thought about the information puzzle. The real question is, how do we relate the hot and cold pictures and somehow believe in them both at the same time? Or are we supposed to take one of the two pictures as more fundamental? Is the black hole fundamentally a statistical mechanical object evolving by some quantum mechanical Hamiltonian H that in gravity should be measurable to infinity, which is the ADM mass, in which case you might think that such an object would look thermal from a macrostate perspective due to the inability to measure the microstate degrees of freedom, which are S equals A over 4G. From this perspective, you might expect the information to continue to be accessible outside by analogy to unitary quantum mechanical systems. Or is the black hole fundamentally a cold, out of equilibrium object with entanglement given by the Q of T in curved space-time formula, which only seems to be hot when you make the artificial restriction of ignoring the interior of the space-time. From this perspective, you might expect the information to stay inside the black hole by causality. So the question is, oops, I guess I said paradox here. Sorry, Ted. I know you must be so disappointed. What does it actually mean to solve the information puzzle? So because there's been such a significant amount of discussion, I think we should actually need to disentangle the question into a variety of sub-questions and maybe say we have done better to try to answer some of the questions than the other questions. So the first question, which is a lot of the controversy, is the question, is the information that falls into a black hole lost permanently, or is it preserved even from the perspective of observers who stay outside the horizon? Okay, now, one key observation about this question is that it at least appears to be a binary choice. To answer this question is to decide yes or no on information loss. Now, the large majority of current research in high energy physics, especially among string theorists, presumes the answer is no, information is preserved, but some notable dissenters who tend to be relativists exist, including we have Bob in the audience here, who will, if you talk to him after the talk, I'm sure will be happy to defend his view vigorously. Okay. Now, because this is a binary choice, maybe it's not the most interesting question because, you know, if a genie tells you the answer is yes or the answer is no, you maybe aren't just completely satisfied that there's nothing more interesting to learn. The interesting questions are what happens after you answer yes or no. Okay, so Ted, of course, has answered both yes and no because he's a time-dependent object. And so I was actually privileged to be his PhD student at the time he changed his mind. He had formerly persuaded me that information was lost temporarily, but I was never as diehard as him, and I was always more sympathetic to this holographic perspective. So I think it's more meaningful that he changed his mind as a result of an argument by Don Meros that I'll present in a moment, which is related to this question I'll say. So you have a choice. if you believe information is lost, then the follow-up questions are question 2, how can this be reconciled with the fact that in gravitational systems, the quantum Hamiltonian H is a pure boundary term at spatial infinity? I'll give a more precise statement about why this is an issue on the next slide. Or more concretely, if you have a specific holographic duality, such as ADS-CFT, where the boundary CFT seems to have a Hamiltonian that explicitly involves a unitary matter, so that all the information remains present on the boundary. The question is how you choose to disagree with this is question 2. So whether you think the CFT doesn't fully describe the bulk, or whether there's some subtlety in the dictionary, you have to actually say what the thing is that gives. Okay, and another question. Question 3 is, if you think information is lost, then how do you construct a non-unitary analog of the S matrix, which takes into account, for example, the possibility of black holes as intermediate states? I think it's probably true that if the information loss theory people were able to actually give us like mathematical equations for this non-unitary S matrix, that people would find that perspective more persuasive. There were some papers arguing it's impossible, but there might be loopholes in that. So the real question here, though, is not to argue against the impossibility, but to actually provide it in some, situation, I guess, or some theory. Okay, so there we go. All right, so what's this argument from that Don Meroff gave that persuaded Ted? So it goes like this. And well, there's an analog of this argument for asymptotically flat. It really works most easily if you assume asymptotically ADS. So let us assume ADS, which means that we have a time-like boundary. But very importantly, we are not assuming as a premise ADS-CFT. We're going to try to get a conclusion that's reminiscent of ADS-CFT, but our premises are GR and quantum mechanics and this asymptotically ADS boundary. Okay. So the interesting about this argument is it really is a quantum gravity argument in the sense that if you deny either quantum mechanics or general relativity, you can easily escape from it. So you really need both. Okay. So the idea is that in the asymptotically ADS boundary, you can define something like an algebra of observables that exists. Well, maybe you want to be careful and not say at exactly one moment of time because quantum fields need to be smeared, but you could take some small time interval and then ask about the asymptotic boundary conditions of fields, say a scalar field or something that is on the algebra. So it seems intuitively there should be some set of things that you're allowed to measure forming an algebra at time t1 with a small interval around it. And at least in the context of perturbative QFT in ADS, it seems like this algebra should include things that excite fields that then fall into the ADS. So we could send some scalar field pulse, and if the scalar field has sufficiently high energy, it could collapse to form a black hole. And if that black hole eventually evaporates, then we have a Pernos diagram that looks like this. Okay, but the question is, where is this information lost? And to address this question, we take another algebra of observables. It's the time translation of this at some significantly later time. So that's the algebra at time t2. And the argument goes like this, that if you're in the algebra t2, that one of the observables another observable that should be measurable in this algebra is the Hamiltonian, precisely because gravity tells us that on shell, the Hamiltonian is a pure boundary term, and it can be measured by the ADM formula out at infinity. So if we assume that this algebra contains the Hamiltonian, then it seems that we can time translate observables by conjugating with e to the I h delta t either minus IH delta T on both sides to get to translate from one to the other. And that means that this observable that excited the scalar field, you could imagine encoded a bit of information, say whether the pulse of the scalar field had positive or negative amplitude or something, then that information, whatever is in this pulse, would seemingly be recoverable at the later moment of time just by using this expression. Okay, yes.
Just one question. If you consider this argument in which you include the boundary Hamiltonian in the algebra, then I guess you don't have information loss, but you also don't have a page curve, right? You have a flat page curve.
Right, so this argument actually shows that the information is always available. So it does not, in fact, immediately get you the page curve. That's correct. You'd probably need to do some coarse graining of these boundary degrees of freedom. Other questions? Yeah, well, the equipment may have its own questions. Perhaps it's on Bob's side.
Small black hole, large black hole matters. The large black hole.
I don't think it matters a lot. Of course, I did say it evaporated. So the large black holes won't evaporate on their own, although it doesn't really matter whether it evaporates to do this argument. You could do more subtle things where you slowly extract information by coupling the boundary to some auxiliary system, although that's a bit, well, it could be unitary in the joint system. Okay, so that was Don Merrill's argument, and it persuaded Ted. Okay, so now if we accept this answer to question 1, it doesn't mean that we don't have follow-up questions. We still do have follow-up questions. In fact, I have one more on this slide than on the other option. So here are the follow-up questions. One question is, what went wrong with Hawking's original semi-classical calculation that the black hole radiation is in a thermal state? If in fact the total state of the system is not mixed but pure, assuming that the black hole formed from pure collapse. Another question is, what is the physical mechanism by which the information escapes from the black hole if instead of thinking about the boundary, you think about the bulk? And the fourth question is, how do you recover in appropriate settings the experiences of an infalling observer who sees a vacuum state? Now, my claim is that unless you can answer all of these questions, you're not allowed to write news articles that say information paradox is solved.
Verification about question 3, do you mean that in terms of as a function of Lorentzian time?
I mean, it's a little bit vague. One of the things about these questions is sometimes you don't know how it should have been phrased until you know the answer, of course. But the question is, I mean, to see the questions 2 and 3 are distinct, you could say that even if you have evidence that Hawking's calculation was wrong, that doesn't necessarily tell you what information exactly escapes and what form is there.
Yeah, I guess, would you consider a Euclidean graphical wormhole calculation?
I'm going to mention this, so I'll wait for it. Okay. Okay. So my own view of recent progress, I said last 5 years, but I guess I gave the talk in late 2024, so maybe you need to augment that number, on the information puzzle, is that the main advance consists of getting better answers to questions 2 and 3, conditional on a holographic understanding of why the information is observed. answer 1. But that question 4 still remains very confusing for a reason that I will try to identify at the end. Okay. So suppose we phrase the question as what went wrong with Hawking's original semi-classical calculation that the black hole radiation is in a thermal state. Okay. So, and what's the new development? So if you could plot the time, as time goes on, you can look at the entropy radiated from the black hole, and that increases, and it isn't exactly a straight line, but we could parameterize this in a way where it is. And so in Hawking's original picture, the entropy just monotonically increases up until the point where the black hole is completely evaporated, after which time you have a bit more entropy than the A/4G of the original black hole. A bit more because Hawking evaporation isn't a perfectly adiabatic process. So you have a little bit of entropy production as it happens. On the other hand, if you believed that the final state of all the Hawking radiation is pure, then Don Page argued that you would generically expect something like a curve that goes up until you have about equal entropy between the outside system and the black hole, and then it'll go back down again. And although it's a little bit curved at the top, you could argue from taking like random subsystems of quantum systems that you, in the limit of a large number of degrees of freedom, you pretty much expect it to match this curve up until the point where it turns around. Okay, now we used to take for granted that semi-classical physics predicted the blue line, and that the question was just whether some non-perturbative quantum gravity argument gives you the red line. Okay, but we now know, this is the new insight, that there are ways of asking semi-classical gravity the question where it seems to predict the Page curve, the red line. So as an example, there's a formula for the entropy of a holographic formula for the entropy of the space-time, the quantum extremal surface. And as first shown by Pennington, but there is also these other papers that had a very had a similar form of the argument at around the same time. You can actually show that there's a phase transition in this formula that gives you, at least if you take it literally, the Page curve. But since this formula that I didn't write down can actually be derived from the semi-classical gravity path integral, you can also look directly at the semi-classical gravity path integral, and it seems to imply that somehow, in some sense, knows about the information coming out. But the sense is subtle, okay? So I would phrase it like this. The semi-classical gravitational path integral knows that information comes out of the black hole. So it knows that the information is preserved, but it doesn't know how it is preserved, okay? What it behaves like is an ensemble of lots of different scenarios in which the information can come out, where you're somehow tracing over all of those scenarios to get a mixed state. But so if you ask the semi-classical path integral, what comes out of one black hole? What it does is it guesses a random highly mixed state, but just like Hawking's original calculation. But if you consider two or more identical black holes, and then you consider processes that swap the two states of the black hole to see whether the things that come out are the same or different, then the gravitational path integral, if you allow these topologically non-trivial connected baby universe type constructions, if you take those seriously, it seems to tell you that the two states of the system are the same as each other. And so this is the replica wormholes calculation that was, again, done by two different sets of people on the West Coast and the East Coast. So the picture is not that semi-classical physics knows how the information comes out, but rather that you can ask it the question in the right way, where it seems to drop the hint about the it coming out. Okay, so so that is maybe a start towards an answer to a question. You have a
So that's, you know, some sort of answer to what is wrong with path integral like derivations of this. Okay, but the way you phrase the question is a much more interesting question of what is wrong with Hawking's original calculation, which was a quantum fields in curved space-time calculation, and you know that certainly does predict information loss. I mean, and the ingredients going into that is treating the black hole geometry classically and treating the quantum effects as quantum fields in curved space-time. But I mean, where did that go wrong? Is space-time highly non-classical when you form a black hole? Or is quantum field theory in curved space-time a terrible description? I mean, there's some...
Right. Well, I mean, on a literal way of taking this calculation, it would say that you're omitting terms that should be there in the gravitational path integral that presumably mean that the calculation...
Nothing to do with your quantum fields and curved space-time calculation.
Well, like I said,
Something is wrong with that. It'd be very interesting to know what
you may well be you're probably correct that there's more juice to squeeze out of question 2 than what this thing is saying. You don't have to say that that this is a complete answer to question 2. Rather, the claim is that in some sense, we're agreeing with Hawking's original calculation when it comes to the ensemble of possible things that will come out, and these calculations suggest a different interpretation of that.
I mean, I think, I don't want to hold you up anyway, but it's using Hawking's original calculation. We're talking about a calculation that came 3 or 4 years after Hawking's original calculation that doesn't have the grounding in quantum field theory and curved space-time that the original calculation did. But anyway, I don't want to...
Can't you say that the missing ingredients was... Can't you say that the missing ingredients was topology change? So that was a quantum field theory on top of a fixed background calculation, and this calculation requires topology change.
Does topology change in gravitational collapse then? As a star is collapsing, it changes its topology? I don't understand this, but I think I've spoken long enough. I mean, I could reclaim my extra half hour. The Hawking's original calculation has nothing to do with entropy.
Well, this curve in right there, you plot the entropy.
Yeah, I know that's what you deduce from his original calculation. His original calculation did not calculate any entropy.
Well, it calculates a QFT state, and then you could ask what entropy it has.
Right. So what's wrong with the QFT state is the question. Anyway, we'll talk later.
Okay, yeah. So yeah, actually, Bob and I once were invited to debate information loss at something called Seven Pines. So that was a lot of fun. And then later on at Cambridge, people asked to hear my talk again, not this talk, but one that was, arguing specifically for information preservation. But I thought it was very unfair for me to give that talk one-sided since I, wasn't even presenting the other side because I knew Bob would do it. So I asked Bob for permission to give his talk too, and he kindly agreed. So maybe, okay. We'll give this talk. All right, now what about question 3? What's the mechanism by which information escapes from the black hole? And again, if you accept this sort of holographic perspective, and so if we go back to Don Merrill's argument, it's important to note that in terms of all the boundary degrees of freedom, if you accept this argument, then the information is not, in fact, lost even temporarily, because the information is always available on the boundary algebra, which remains pure. But there's a closely related question, which is how this pure state at late time arises and relates to some sort of nice slice in the black hole interior, where a nice slice is something that cuts through this diagram and includes all of the interesting parts, but stays sufficiently far away from the singularity that there's nothing Planckian about it. And in particular, if you accept a holographic view of physics from the get-go, where somehow information is always encoded on your boundary of your system, you might be tempted to say that the nice slice, which has a geometry something like this, because it gets bigger as we go out to infinity, but there's some long period of time where it has approximately the same area here, and then it closes off at the origin on this side, and here's like the initial pulse falling in right here like this. Okay, so people try to construct various toy models or of quantum gravity, things like tensor networks, where it's sort of manifest that the information on this slice flows out to the boundary at infinity. Similarly, I've worked on something called Cauchy slice holography, where you do a TT bar deformation to get a theory that's on this slice. And again, although this time it's in a continuum theory, it would have the property that's manifestly true, that if you have only one boundary, that this is like a partition function with just one boundary, it gives you some pure state on the boundary. So the idea is, in a sort of local holography viewpoint, we would try to write down physics in which it's just manifestly true from the beginning that any information flows out to the boundary. And then the question turns into why do you get keeping track of that information? And in particular, if you note the place where this nice slice crosses the horizon, at that point, we know what entropy to associate with that, which is e to the a over 4. And you can argue that at this point of the process, there should be a bottleneck where you have a Hilbert space here associated with this horizon that contains at most e to the a over 4 states. So this could be by construction in some sort of tensor network model. In Cauchy slice holography, I have papers with Ranaxoni where we explicitly counted the number of states. And this is just how many there are at that point. So ultimately, because it's a deformation of the CFT, which has a discrete spectrum of states. Anyway, whatever, on a model like this, which of course Bob would disagree with the very premises of the model, since it's manifestly boundary, the information is all in the boundary. But on a model like this, what happens, okay? Well, we can also draw the Hawking radiation and the partners in this diagram. And at some point, what happens is that if you take the entropy you're trying to reconstruct, maybe it's actually mixed, of this infalling object, and you take the entropy of all of the partners, it gets bigger than this bottleneck, okay? So somehow the information that is behind this thing on the nice slice, there's too much information to fit through just E over A over 4 states. And that's precisely the point where something new has to happen, is forced to happen in a model like this. So precisely at the point where you turn around, that's precisely the point where there's too much stuff behind the horizon to be encoded on the horizon. And as far as I can see, the only possible solution that is compatible with purity is if the theory that lives on this Cauchy slice performs a post-selection. So it takes a bigger number of states and it projects it down to a smaller number of states. A post-selection is a quantum projection that behaves a lot like a measurement, but if you forced one of the possible outcomes of that measurement to necessarily happen with probability 1. Now, there's some discussion of this in tensor network models called Python's lunch. This is the paper where we calculated the number of states. There's a somewhat related idea due to Horowitz and Maldacena, where they suggested that you could have information come out because of post-selection on the singularity. This idea is in some way similar to that idea, but it's also different because we say that it is only at the horizon. It has nothing specific to do with the singularity, and the post-selection occurs no matter where you slice this thing. Okay. So this connects again to the idea that maybe when you take into account the full gravitational path integral, you find that there's some more non-local constraints besides the local Hamiltonian constraints. So there's sort of fewer states in the non-perturbative quantum gravity than you thought there were going to be. There's a number of also a nice paper by Dan Jaffers I didn't cite. Okay, so but does this answer question 4, which is really what the we need? Okay, and there we have the now famous firewalls paradox of the AMPS paper, where the problem is that you take the early quantum Hawking radiation, the late Hawking radiation, and the late partners, and we have good reason, if you think information is preserved, to think the late Hawking radiation is nearly maximally entangled with the early Hawking radiation. But we also have reason to think from the infalling observer who sees the cold black hole that the late Hawking quanta should be entangled with the partner modes. And of course, you could rephrase this in terms, Bob's arguments for information loss are basically going to be prioritizing this entanglement and then saying it's incompatible with this other entanglement. So the firewalls paper set it up as a violation of Strong's subadditivity. There was some earlier work I should probably have cited here by Samir Mathur that was really saying similar points before that. Okay, so the firewalls paradox assumes that all 3 of these subsystems, the thing we're trying to reconstruct, the partner modes, and the late Hawking radiation are all independent quantum subsystems. So what I'm arguing is that if there's a bottleneck, if there's some kind of post-selection, then they're not, in fact, independent subsystems. This thing and this thing are sort of forced into some specific entangled state, and in a way that is analogous to quantum teleportation, it pushes the information out to here. So that's the picture I believe is true, and that raises the question, if this picture can be made mathematically precise, perhaps by giving some fully UV complete description of this TT-bar deformed theory or some tensor network or whatever people are trying to, would it count as solving the information puzzle? Would it count? Would it be an acceptable solution? And I claim the answer is no. There's still a mystery that would remain. You're not allowed to say yet that you've solved question 4. Okay. Okay, so why do I say the answer is no? Because to predict the experiences of an infalling observer, we would need a way to interpret quantum mechanics in the presence of some expected post-selection effects occurring. Okay. And my standards are that the picture has to at least make as much sense as the Copenhagen interpretation of quantum mechanics. Now, we all have these philosophical arguments that Copenhagen is like half-assed thing because of the separation between the classical observer and the quantum. But if you can't give me something at least as good as Copenhagen, then I claim there's a big problem. Okay. So, and in fact, people studiously avoid using most people who aren't brave, doing quantum mechanics in a way that is isomorphic to this. Because it is true, even if you don't do post-selection, that we still do regular measurements. And when you do a regular measurement, you've learned something about the universe, and you could pretend you post-selected onto whatever it is that you measured, okay? But in normal quantum mechanics, we only do the following thing. We prepare a state, an initial condition, an initial wave function. We let it evolve for some time. We measure it, we predict probabilities for different outcomes by the Born rule, and then we're allowed to use the collapsed state, psi final, as an initial condition in a new experiment. Here's what the standard QM textbooks will scrupulously try to steer you away from and not have you do. Prepare a state at an initial moment of time, let it evolve for some time, project on to some final state, psi final. I don't actually care whether it's a magical post-selection or an experiment here. Let's just say it happened. We get some definite answer. And now give me probabilities for various things that happened in between the initial and final time. That's like a question that we've made taboo to ask, okay? And there's some brave people who've tried to study it with something called the time symmetric formulation. That's because you have both an initial and a final state, but it's tricky problem. There's something called the 3-box paradox, for example. And to me, it has the flavor of a sort of interpretation of quantum mechanics problem. Why do I think that? It's because even before black holes came along, we still really needed to face this problem to do science, to do historical science. Because the main thing is I believe there were dinosaurs, okay? So you learn about dinosaurs when you're a kid, and it's before you learn about quantum mechanics. So I don't want to give up dinosaurs. But we start with some theory about the initial universe, that we have some state that's post-inflation. And we believe this theory on theoretical grounds. So that gives us one state in a vector in the Hilbert space. Then we do present day measurements. It's true we don't measure literally everything. We measure some of the things. If we did measure everything at the present moment, that would give us another vector in the Hilbert space. And these are not, in fact, the same vector in the Hilbert space. They're nearly orthogonal vectors because the probability of any one specific outcome is very small given this initial state. But we believe in this because we see it. Famously, this is not enough to get the second law of thermodynamics. We only get the second law of thermodynamics if we also assume the universe started in some low entropy state, which means perhaps in some specific state. So we have a present day observation. We have a simple initial low energy initial condition. The projections onto these two facts do not commute with each other. So we somehow know more about the universe than is allowed by the Heisenberg uncertainty principle. And we needed both of these facts to know that there were dinosaurs, okay? Because if you start with the state right after inflation, you evolve forwards in time, there's a lot of contingency. Probably there's no Earth. Probably there's no dinosaurs. On the other hand, if you just start with the dinosaur bones and evolve backwards in time without the assumption of a specific initial state, again, you just get the bones keep decaying because entropy goes the wrong way. Okay, so to get the dinosaur, saying there are dinosaurs is somehow synthesizing two propositions that don't commute with each other. Now, my idea is maybe describing the infalling observer is no harder, but also no easier than this wickedly hard but already important interpretation of quantum mechanics problem. Okay, now, just to say some of the paradoxes that have when you do it, or to say what goes wrong if you do something very naive. It's tempting to say something like, dinosaurs existed at some time if, when you look at all the histories from the initial to the final state, all of the ones that don't involve dinosaurs destructively interfere with each other. So either perfectly or maybe to some accuracy, because we are willing to say it's only nearly certain that there are dinosaurs. So the problem with this rule is that at least if you took this criterion literally, there can be orthogonal projection operators that end up being simultaneously true. Okay, so this is the subject of the 3-box paradox. So you start with an initial state, you take some equal superposition to evolve to A, B, and C. Now there's various things that could happen by only drawing the matrix elements of of the things that contribute to go to the final state. So we can set things up so that the final state is a superposition of these things. And then we can say, we know we started in this initial state. We know we measured this final state at the end. Okay, let's just say we did. We repeat the experiment enough times until we get one where we do measure this. Okay, and then by this criterion, so there's some electron going through some apparatus. Okay, so the path through B and the path through C, I have a minus 1/3 and a plus 1/3. These destructively interfered perfectly with each other. So we assert it's definitely true that the electron is in box A. Also, the path through A and the path through B destructively interfere. So it's also definitely true that the electron was in box C. Now, maybe that makes you uncomfortable to say that it's definitely true that it's in box A and definitely true that it's in box C. This is not the sense of it goes both ways of the two-slit experiment. This is like saying you could have thrown out both box B and C and get the right result, and you could throw out both box A and B. So it's like it's +1 here, +1 here, and -1 here. It's like it's negative true that it's in box B. Okay, so this is kind of crazy. I don't know whether we can turn it into a consistent picture of the world. There are various other things that projection operators that are orthogonal to the dinosaurs existing that are kind of very gerrymandered that also have the property that they would be true by this criteria. Anyway, I'm not claiming to have solved this problem. I'm just pointing out some of the conceptual issues with it. Okay, so in conclusion, my proposal is the following answers. First, information is preserved by boundary unitarity. Second, semi-classical gravity knows that the information is preserved, but you need non-perturbative quantum gravity to know how it's preserved. 3, that information gets out of the black hole by means of post-selection. I think it's the only option that's left to us unless you want to join Bob and try to answer my other question 2 and question 3. And I propose that the black hole interior and the infalling observer is isomorphic to dinosaurs. Okay, so, and also that the information, sorry, Ted, puzzle is still interesting. All right, thanks for your attention.
Thanks, Aron. Questions for Aron?
There are many aspects of your talk I could ask you about, and I may later, but the one I'm going to ask you now is when talking about replica wormholes, you took very great care to say that what semi-classical gives you is like saying there's an ensemble, blah, 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 blah. Why did you not say semi-classical gravity gives you an ensemble or a set of super selection sectors or words one might like to use?
Okay, maybe because I'm skeptical that it's true. Because it seems if that were true, you would need, if you say something like there's a gazillion string theory vacua that are observationally indistinguishable, even if if it's a finite number, I could make a black hole that's big enough, and the e to the A/4 is bigger than the number of consistent UV quantum gravity theories I have.
Talk more later, but there's clearly an principal difference between what semi-classical gravity might give you and what string theory vacua might exist. Those seem like very different questions to me.
Well, if the statement is it's an ensemble over if it's an ensemble over a set of non-perturbatively consistent quantum gravity
That would not
microphysics.
be the
Maybe you
correct
think it's a different type of ensemble. Is that where you're going with this?
For example. But I do think it's what semi-classical gravity gives you. Whether there exists a UV completion of it is a different question.
I mean, I don't think if you take n equals 4 super Yang mills and you you collapse a black hole and you get a pure state out, I don't think there actually are lots of different possible pure states that could come out. I just think semi-classical gravity doesn't know which one comes out.
I agree with you. I still think semi-classical gravity gives an ensemble. We can talk more later. N equals 4 super Yang mills is smarter than supergravity, than semi-classical gravity.
Yes.
Right.
That's the other mic.
Hi. Oh, I'm over here.
Yeah. Yeah.
I'm curious. In a what if people? So if I'm an observer, like inside the black hole, and there's post selection, does that mess with my arrow of time or anything, or how does that work if there's a definite?
That's a good question. I mean, if we can get definite probability predictions and interpretation, then of course the next question is, does it agree in some regime with what semi-classical quantum field theory and curved space-time told us? But before you can even ask that question, you need to have a tool for making predictions. Okay, so I don't understand it well enough to answer the question, but I agree your question is interesting and worth asking if we could answer it.
Thanks for the talk, Aaron. There's another way of thinking about the page curve. Hello?
Hey.
Okay, thanks. There's another way of thinking about the page curve question, which is maybe related to some things that Ted has written about before, which is, okay, yeah, there's this boundary unitarity argument, which says that the information is always accessible in the exterior near the boundary. But before the page time at some point, a bunch of radiation has come out, but the information is somehow not in the radiation. You have to access the entire boundary. You have to access some degrees of freedom that are outside the exterior, but not describing the radiation. And Ted has called these nebulons. There's this idea that you have radiation and nebulons, and at some point before the page time, the information is all in the nebulons, and after the page time, information gets transferred to the radiation, so you can read it off with the PETS map or something. So how? I guess my question is, in your view, what would the nebulon degrees of freedom be, and how is this information transfer implemented by post-selection?
The nebulon one is the one that is the radiation, or the one that
it's not radiation?
It's not the radiation.
Yes.
Right. So I guess it's something like if it's like n equals 4 super Yang mills, it's something like a deconfined blob of gluon plasma or something that has a large entropy. Whereas the stuff describing the radiation is like a bunch of separate color singlets or something.
Well, no,
I mean,
Who invited you to this?
if you want to, I didn't normally think of it in terms of holography, but let's do so. So we're talking about, let's say, a pure state that should have zero entropy. So you injected some energy into the CFT, it thermalized and it looked very much like a thermal state. But the very fine details about that state that show that actually it's pure and it's not a mixed state are encoded in the dual in some way. And that way is the nebulon way. What is the nebula? What are the nebulons? I feel like they can only be the fine-grained structure of the multiple moments of the gravitational field or something that you don't think of them as radiation. One paper which came closest to specifying what they are from what I've seen is by Survat Raju, where he sort of wrote down a collection of correlation functions with many, many operators in them, including the Hamiltonian at the boundary. And sort of the collection of all of these correlation functions with very fine-grained information would be needed to capture this information. So, and that's certainly not just captured by looking at the radiative modes of the gravitational field. It's more like it's structure you couldn't possibly capture within quantum field theory and curved space-time, just in a background space-time description of the Hawking process. Anyway, I haven't given up that view yet, but I'm open to hearing that it's an incoherent view.
Could you briefly explain what post-selection is?
Right. So let's say you have a projection operator in your Hilbert space, okay? And so I have some vector in my Hilbert space at some moment of time. When I perform the post-selection, what I do is I first project my state onto that projection subspace, and then I normalize it so it's a unit vector again. That's it. So it's precisely what I do if I do a measurement in the Copenhagen interpretation, but only condition. It's what I do in Copenhagen conditional on getting that particular answer. The thing that makes post-selection different from measurement is only that I'm forcing one particular outcome for the measurement. So it's from the perspective of a normal quantum mechanics system, that's what makes it magic, what you couldn't actually do. At the same time, I argued that from an interpretational perspective, it's actually not that different from the question of what we would do if we just condition on getting a particular measurement and then ask about the past.
I wanted to ask about your answer 3 in
Yes.
terms of post-selection. The reason why before I asked if you meant question 3 as a dynamical in Lorentzian time question is because it sounds to me like this answer in terms of post-selection has to do with some kinematical statement where you, even the way you framed it, if I understood it correctly, a kinematical statement about how you map the information from the inside of the black hole to the outside, slice by slice in a snapshot in time.
By kinematic, you mean on one slice? Then yes.
Yes. Then I would have thought that a satisfactory resolution also tells you how dynamically the radiation gets out, which might involve some quantum gravity effects we don't know about. And maybe that's also why this is unsatisfactory from the point of view that Bob was talking about.
Perhaps, I mean, once you can do it on one slice, then you also want to do it on multiple slices and compare those answers. Yes.
Yes, but what I'm trying to say is it really solved? Is it really answered that question, or do we need to really understand what's going on from a dynamical point of view as you evolve in time? How that
I mean, I have some thoughts about what's going on dynamically in terms of like the generalized second law. So one statement you could make is that the generalized second law tells you that if you don't care about the partner information and you're just prepared to use the partners and the Hawking radiation as a resource, so you think of it as creating like extra tensor network legs between these two systems. If you think of this as just a resource and your goal is just to reconstruct what came in, there's never a bottleneck. You can always do it. The generalized second law tells you that. The dynamics, of course, are part of what tells you that these things are in a particular entangled state. Okay, it's if you get greedy and you say, I want to check that this is entangled, and I also want to reconstruct this state. So I want to reconstruct that felon, and I want to explicitly check that these partner modes are in the right state, entangled with these things. Then you aren't allowed to use this as a resource anymore. And that's when you're forced to do post-selection. I'm hoping this is related to how you still get the semi-classical picture, is the fact that you, as long as you ignore these partner modes, you don't have to do this post-selection.
Okay, my question is, imagine we have solved quantum gravity and we have a full control of the quantum gravitational.
Okay, good, done. Go on.
The quantum gravitational degrees of freedom, so that I can describe the evaporation of the black hole at the full quantum level, both gravity and matter. So imagine also that initially we assume that the state can be factorized in gravity and matter, right? So my question is, would you expect that as the black hole evaporates, the factorization keeps holding?
I mean, no, because the Hawking radiation comes out in a way that is dependent on the geometry of the
Right,
case.
but then-
so I don't see how it could remain independent.
Okay, but then there will be always correlation between the Hawking quanta and whatever are the quantum gravitational degrees of freedom. So why we hope that the information puzzle can be solved by semi-classical gravity, where you give up basically the quantum description, right, of gravity. You have just
I
classical
mean,
space-time.
the black hole has gravitational degrees of freedom, so you might expect there's microstates for what the black hole is. That's part of gravity in the sense, you got black holes with slightly different masses is one very simple example.
Yeah, but you really believe that you can recover this way these correlations between the quantum gravitational degrees of freedom and the Hawking quanta, because you basically say that it doesn't factorize anymore after a while. So
this is one reason why people often talk about let it completely evaporate so that you don't have the black hole to deal with. But of course, when we talk about things like Hawking radiation, you would have to include things like gravitons, which of course practically would be almost impossible to measure. But so the gravitational degrees of freedom does include things like gravitons. And that's part of the Hawking radiation.
You take a last question there.
Regarding my previous question about the nebulons. Okay, if the nebulons are the full pure state, thermalized pure state of the n equals 4 theory, and then some color singlets of the radiation, what is the post-selection condition that needs to be?
Well, I don't think the post-selection happens on the CFT.
Okay.
The CFT is just unitary. The post-selection occurs on the Cauchy slice as you evolve the information in a space-like direction, which you must do if you write down a manifestly holographic formulation.
Okay, but if you just look at if you collect the radiation near the boundary, and you are just asking as time passes, instead of evolving across the Cauchy slice, if you want to ask as time passes how information gets into the radiation, you're saying this is not explained by post-selection?
I think it's if you want to keep track of the full bulk dynamics, including the region inside the black hole, and you want to ask how is that compatible with the information coming out post-selection is my answer.
I see. Okay, thanks.
Let's thank Aron again.
Okay, so this concludes the conference portion of the presentation portion of the conference. I want to remind you now we have at 7 p.m. A banquet. So just to remind you on the details, if you're registered for the banquet, you should have received an email last night or a couple of days ago as well with some of the information. But the banquet starts at 7 p.m. It's at Busboys and Poets in Hyattsville. So just a reminder, please only attend if you registered. If you didn't register and you have changed your mind and would like to attend, please come see me. We might have 1 or 2 slots available, but make sure to let me know if you'd like to attend. And when you get there, there's going to be a specific table reserved for Ted and the speakers and a few other people. So if you received an email saying to sit at that table, you should sit at that table. In other ways, there'll be other tables there. So that's that's that. Okay, so I think I want to wrap it up. I just wanted to give a few thanks again. I want to first start out by thanking all the speakers. Thank you so much for giving these talks and honoring Ted. It was a really great conference. Thanks. Oh, yeah. Yeah, thanks to the session chairs for chairing it. It helped, keep the thing run smoothly. Again, thanks a lot to the University of Maryland Department of Physics and the Maryland Center for Fundamental Physics. They were generous in providing funding so you guys could have treats and go to the banquet and have lots of fun. So thanks a lot to them. And finally, I wanted to mention some of the co-organizers who did a lot to make this happen. So first of all, thanks a lot to Raman Sundram, who was really helpful at organizing things on this side over here. David Mattingly in the back has been helping us, and you'll be hearing more from him tonight. So he has a special role tonight. And big thanks to Batul Bana Hashemi and Stefano Antonini. They were so helpful just on all of the details and organizing. I could always just ask them, like, how should we do things? They were always available. So I really appreciate you guys helping run the conference here. So. And finally, since this is a conference in honor of Ted, so let's give Ted one more round of applause for all he's done. Like that. Okay, we'll wrap it up there, and then we'll see you all at the banquet.